Wow, we've been talking about the number a lot, haven't we? And we're forgetting to talk about the unit. I never want you to forget about the unit, so let's go back to that. Whenever you have a measurement, remember, you must have a number and a unit. Without an associated unit, the number of the measurement is meaningless. I'm going to say that again because students leave off the unit so much that I think it's worth saying twice. Without an associated unit, a measurement is meaningless. Now in science, we tend to use the metric system as units for measurement. And the standard units of measurement in the metric system are the gram for mass, abbreviated as lowercase g, the meter for length, abbreviated as lowercase m, the liter for volume, abbreviated as capital L. I don't know why they decided to use capital for that, but they did. In time, we use seconds, abbreviated as just a lowercase s. And for temperature, we can use either Celsius, which is degrees C, or Kelvin, which is just capital K. So those are the standard units. You might live in a country that uses other units. For example, I live in the United States, and for mass, we often use pounds or ounces. We're going to talk about how to convert those to grams. In science, we pretty much always measure things in grams, meters, and liters. We very rarely use measurements like a cup of liquid or a tablespoon of liquid. So it just depends which country you're in, which units you might routinely use around your house. But in science, we've agreed internationally as a group of scientists that we're all going to use the same types of units. Now, a gram is not a very large quantity, I suppose. Well, I guess it could be a large quantity if you're talking about a diamond that weighs a gram. But we can modify these units using prefixes for the metric system to show numbers that are very large or very small. Here's some that I think you should know. The prefix mega, which has the symbol capital M, is the equivalent of 10 to the 6th. So if I had a megameter, that would be 10 to the 6th meters. If I had a megagram, that would be 10 to the 6th grams. You're probably more familiar with the kilogram. That's used to weigh people's body mass, for example. And that's the gram times 1,000. I don't use deci very much, honestly, but centi gets used a lot in measuring length. The centimeter is smaller than the meter. In this case, it's 1/100th of a meter. So there's 100 centimeters in a meter. So it's a meter times 10 to the minus 2 if we're using scientific notation. Other common prefixes that get used to show very small quantities are milli, which is the 1 out of 1,000, micro, which is the unit times 10 to the minus 6, and nano, which is the unit times 10 to the minus 9. Sometimes in chemistry we go even smaller than that. We might use pico, P-I-C-O, which is a lowercase p, and that's the base times 10 to the minus 12. It would be really tedious to write that number out with all of the zeros, so I'm not going to do that. That's part of the reason we use scientific notation. If you're from a country that doesn't routinely use the metric system, you might be used to dealing with measurements like yards and miles. Perhaps you use pounds or quarts. So I want you to think about which of these is larger. What's longer, a yard or a meter? Which one's longer? A meter is longer than a yard. How about a mile or a kilometer? Which one of those two measurements is longer? So again, I've got two measurements. They each have a number of 1, but the unit is much different. So which one's longer, the mile or the kilometer? Hopefully you realize that the mile is longer than the kilometer, but if you live somewhere that doesn't use miles, you might have no idea, and that's okay. These are crazy units we use in the United States. An inch is larger than a centimeter. It's about 2.54 centimeters. A kilogram is heavier than a pound. Sometimes people in the United States have trouble with that because many people in the United States seem to know that a mile is longer than a kilometer. And then when they get to kilograms and pounds, they get confused. How about this one? Hopefully everyone can do this one. Which is larger, 1 milligram or 1 microgram? Those are both pretty light weights, but hopefully you said 1 milligram is larger. Let's talk about some volumes. Which is larger, a quart or a liter? A liter is larger. How about a liter or a gallon? I buy my milk by the gallon. A gallon is larger. Which one of these is larger? A gallon or 1,000 cubic centimeters? This brings up something that I think is really important to know. In the metric system, the volume of a milliliter, just write that down, 1 milliliter, was defined as the volume of this bounded by 1 centimeter by 1 centimeter by 1 centimeter. In other words, if the length, width, and heights of something is all 1 centimeter, that's a milliliter. So I could draw a little cube, right? And if all the sides are 1 centimeter, the volume inside that cube is 1 milliliter. In other words, a milliliter is 1 cubic centimeter. Sometimes that's written as 1 cc. They often talk about it that way in medicine. So I think that's really important to know. So what I'm saying down here at the bottom, when I asked you about the gallon or 1,000 cubic centimeters, well, that's asking you about a gallon or 1,000 milliliters, which is the same as asking you about 1 liter. So a gallon is still larger. What I was just doing there, although I was doing it in my head, was I was using conversion factors. Conversion factors allow you to switch easily between units, and they can easily be looked up. You can look them up on the internet, or you can look them up in any chemistry book that you have. Probably has them in the inside front or back cover. Here's an example of a conversion factor that I've had to use a lot because I used to work in industry, and I was in the United States where we measured things in gallons and pounds, and we were forming a joint venture with a company in Germany who of course measured everything in kilograms and liters. So all the time I was converting between kilograms and liters, and I memorized that 1 kilogram equals 2.2046 pounds. It's easy to convert using dimensional analysis. For example, if I asked you, what is the mass in kilograms of a 65-pound sack of flour? How would we do that calculation? Well, with dimensional analysis, what we would do is we would start with what we have, 65 pounds, and then I would use a conversion factor. I'm going to write the conversion factor as a fraction. I want the fraction to have the unit that I don't want on the bottom. So I'm going to put pounds on the bottom, 2.2046 pounds. And the unit that I do want on the top, 1 kilogram. So to do this calculation, I'm going to take 65 and divide by 2.2046. And that's going to give me 29 kilograms. I would need to use a calculator for that, but I already did, so I figured it out. The last thing I want to talk about is why do we use scientific notation? Now, one of the reasons I showed you already that we use scientific notation is because it's a very easy way to indicate the correct number of significant figures without confusion about zeros. Another reason we use scientific notation is to not have to write so many zeros when we are writing down very, very large or very, very small numbers. Let me give you some examples of very, very small things. What's the diameter of a gold atom? Do you have any idea? Turns out a gold atom is 2.7 angstroms in diameter. 2.7 angstroms. And an angstrom is 10 to the minus 10 meters. So if I wanted to write the diameter of a gold atom in meters, I would write 2.7 times 10 to the minus 10 meters. I wouldn't want to write all those zeros down. I guess I could. Let's do that. How many zeros would I have to write after the decimal point? I'd have to write 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 7. Did I do that right? I think I did. That's tedious. That's a great reason to use scientific notation. Another thing I hope is a very small number is the concentration of arsenic in my apple juice. What do you think the concentration of arsenic in my apple juice is? Well, the Environmental Protection Agency in the United States says it has to be less than 3 parts per billion. Well, how much is 3 parts per billion? 3 parts per billion is 3 times 10 to the minus 7%. That's not very much arsenic. Hopefully it's less than that. So I'm hoping that my concentration is less than 3 times 10 to the minus 7%. How about some very, very large numbers? Atoms are so tiny, you'll see quickly that if we're looking at even a relatively small amount of molecules or atoms, the number of molecules and atoms can be very large. In other words, if I had a cup of water, how many water molecules would that be? It turns out that would be 8.36 times 10 to the 24 molecules of water in 1 cup of water. Just a little coffee cup. It's a lot. That's a large number. I would never want to write that number without scientific notation because I'd have to write a lot of zeros, 22 zeros, wouldn't I? How about the U.S. national debt? Boy, that goes up and down. So that budget deficit fluctuates, but last time I looked, it was $642 billion, which is a huge number. And I can write that as 6.42 times 10 to the 11th power. Other numbers that are very large are things like populations of countries. If we looked at the entire world, the UN projects the population of the world would be 8.9 billion people by the year 2050. That's their middle estimate. It's not their conservative estimate, which is lower, and it's not their, oh no, overpopulation estimate, although 8.9 billion is probably overpopulation. But 8.9 billion people is 8.9 times 10 to the 9th people. If you write all the zeros down there, you'll see that that's a very large number of zeros. I've enjoyed this review of measurements and significant figures. Remember, measurements contain both numbers and units. Use the correct number of significant figures to show the precision of the number. And be careful to consider how any mathematical operations are affecting the number of significant figures. It's extremely important to keep track of the units, and I suggest writing the units down every single time. If you're not in the habit of doing that, I hope you can change that habit. Finally, unit conversion factors are just ratios, and those ratios can be written as fractions with either quantity in the numerator. You can use those fractions to do dimensional analysis and convert units. We're going to be talking about many measurements in this class, and we're going to be performing calculations and unit conversions routinely. So please take advantage of the practice exercises this week. Wow, we've been talking about the number a lot, haven't we? And we're forgetting to talk about the unit. I never want you to forget about the unit, so let's go back to that. Whenever you have a measure